All right, hi everyone. This is going to be a video lesson for calculus on one-sided limits. And we just had, the previous video was a pretty long one all about limits. And this video is going to be a lot shorter. The reason why it's going to be shorter is because we already talked about one-sided limits a little bit in the previous video. So in this section, we'll review what one-sided limits are. We'll do some practice problems, but we'll keep it a little bit shorter. Okay, so let's get started. Okay, so even though I said this is going to be a shorter section, it's still important. It's still important to us. I want to remind you from the previous video, in our discussion of limits, we had a few definitions. And I'm not going to write the definitions again word for word with every little detail. But let's remember the basic idea of what this means. Limit of f of x as x goes to c equals L. One thing that it means is that x approaches c from both sides. I mean, there's more to it than that. You know, there's stuff about getting f of x arbitrarily close to L, etc. But the point that I'm trying to highlight here is that x has to approach c from the left and x approaches c from the right if we were to graph it. We also talked about writing this same sort of thing, but with a little minus sign. So it looks like this, and we write this minus sign kind of looking like an exponent. It looks like c raised to the minus sign. It's not technically an exponent, but that's how we write it. And this means that x approaches c, and if you remember the definition that we said for this, we said, and x is less than c. I'm going to write that with an inequality symbol this time. I think last time we wrote it out with words, x less than c. I'm going to say here, this is sometimes called the left-hand limit. So we are approaching from the left. And the other one is with a little plus sign. And it means that x is only approaching from the other direction. So x approaches c, and x is greater than c. It's on the other side. This is sometimes called a right-hand limit. In all of these cases, we're saying that f of x is approaching L as x does this. Okay, and the second two cases that we wrote here, this one and this one, these are what are sometimes called one-sided limits. So there's the, original main definition of limit, the limit of a function, but then there's also these one-sided versions. When I say things like approach from the left and approach from the right, you can draw a picture of a graph and you can think of the x-axis. Another way you could think of this is on the number line. The real number line. Let's say there's some number c somewhere on the number line. We want to talk about what does it look like when x approaches c. Sometimes we were drawing this with an arrow. How about this? If I approach from this direction, I'm getting closer and closer and closer to c, but not touching c, not equal to c. Or the other way is like this. And the point that I want to make here is that on the one side, we are approaching from the left. The other side, we're approaching from the right. Okay. Just one little subtlety that I wanted to point out here is that if you're x, let's say you are the variable x, okay, and you're walking along the number line, and you want to approach C. So you're x, you're walking, you're approaching from the left. What direction are you moving in? You're actually moving towards the right. Okay, so if you are approaching from the left, it means that you are moving to the right to get closer and closer to C. On the other hand, if you are approaching from the right, then you are walking to the left. So just keep that in mind. It can sometimes seem a little backwards. But, the first one is called the left-hand limit. We are approaching from the left. We, being x, are on this side. We are less than C. And the other one is the right-hand limit. We're approaching from the right. X is greater than C. So certainly it seems like these three types of limits should be related to each other. We have a theorem about this. And it says the limit as x goes to C of f of x equals L. Now this just says limit. It doesn't have a plus sign or a minus sign. So this is kind of just the limit. It equals L if and only if the limit of f of x as x approaches C from the left equals L, and the limit of f of x as x approaches C from the right equals L. So this is a theorem in one sentence. I'll give you a chance to see that. Let's think about what this says. So the limit over here, this type of limit, this is supposed to be when you approach from both sides. So all this theorem is really saying is the limit from both sides is L, only if the limit from the left side is L and the limit from the right side is L. It makes sense, right? Both sides, only if left side and right side. They have to all equal the same thing. So that's where if you do these one-sided limits, the left one and the right one, if you get two different things, like instead of L and L, if you got two different numbers, then we would say that the limit does not exist. And we saw that happen once last time. Let me show you a little example. This is going to be your example. It's going to be one of these ones where we're given a picture, and then I'll ask a few questions about it. And I think I mentioned this last time, but piecewise functions make really nice examples for limit questions. So we're going to have some kind of weird piecewise function. Formula is not going to be given. Let's see. 1, 2, 1, 2. All right, this is going to be the graph of a function called y equals f of x. We don't have a formula given to us. This is the entire function. And I'm going to ask you to find a few limits. So I'm going to write a few of these. You can wait till I write them all before you start answering them, I guess. And whenever something says to find the limit or compute the limit, it means find it if it exists. If it doesn't exist, then you just say it doesn't exist. Going to be 5 of these. All right, so I'd like you to take a minute and try to find all 5 of these based on the graph and based on our understanding of limits. And this would be a good place for you to pause the video, take a couple of minutes, and see if you can figure these out. Okay, so if we were in class, I would have given you a few minutes here, and I would probably ask for volunteers and stuff, but we're doing this on a video, so let me talk about these, and we'll see if what I got agrees with what you got. As x goes to 0 from the left, and I don't want to draw my little blue arrows here because there's 5 questions, and we're going to get too many arrows, but I'll try to point to things anyway. We're on this function, we're approaching 0 on the x-axis here. We're approaching it from the left, so we're kind of on this part of the curve. We're going uphill from the left, so we're going to the right, and we're going up this hill. It looks like we are approaching a height of 1. We're going up, 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 towards the height of 1. The other problem, the next problem, is asking us to approach 0 from the right. So this time we are thinking of numbers like 0.2, 0.1, 0.01. We're getting closer and closer to 0 from the right. We're going down this hill, down towards a height of 0. That's going to be 0. What's happening here? The limit as x goes to 0. There's no plus or minus, so this means from both sides. And we already did the left-hand side and the right-hand side. One of them gave us 1, one of them gave us 0. The theorem says that the limit can equal something if and only if the left-hand limit and the right-hand limit both equal the same L. We got different things here. We got a 1 and we got a 0. So we say that this does not exist. You could say it's undefined, or you could say does not exist. Because it doesn't equal 1, because that doesn't agree with the other direction. It doesn't equal 0, because that doesn't work with the other direction. So if it's not 1 and it's not 0, it just doesn't exist. Fourth problem, limit of f of x as x approaches -2 from the right. I wanted to give you one that had like a negative number, but also a little plus sign next to it. -2 is over here. Okay? We're approaching, here's -2, and we're approaching it from the right. So we are on this curve. We're going to approach from the right, so we're going to the left. We're going up this hill towards this open circle. We never actually touch that open circle, but we get closer and closer to it, approaching a height of 1. And the final problem, x goes to +2 from the left. +2 is over here. I'm approaching it from the left, which means I'm sliding down this hill from the left. So we're going to the right. So we're going down, 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 down towards a height of 0. This is 0. All right, how about we do another one? Let's do another one. That was a problem where you were given a graph and there were some questions about it. I said at the beginning of that problem that it was a piecewise function, and you know, I think it's because it has these like two separated pieces that makes me think it's a piecewise function, but we didn't have a formula for it. How about I give you one where we're going to be given a formula for a piecewise function, and we're not going to be given a graph. So piecewise function can have 2 rules or 3 rules or whatever. This is going to have 3 rules. This is going to be 1 plus x if x is less than -1, x squared if -1 is less than or equal to x is less than less than 1, and 2 minus x if x is greater than or equal to 1. Let's move this page up. Now, I haven't asked any limit questions yet, but that's the function we're dealing with. Let's evaluate. I think I have 6 parts for this one. So I'll write these out and then I'll talk us through them. This one's going to be x goes to -1 with a plus sign. This one is going to be x goes to -1. And let's get 3 more of them over here. Limit f of x as x goes to 1 with a little minus sign. Limit f of x as x goes to 1 with a little plus sign. And finally, limit f of x, x goes to 1. So what do you think? How about this? How about you pause it, try this out. Take a couple of minutes, see if you can figure these out, and then you can check back with me. So some students find this type of problem to be harder because you're given the formula of this piecewise function. Some students find the other type of problem to be harder where we're given a graph. Just depends on, your own preference. Let's just take them one at a time. Just focus on part A. X is approaching -1 from the left. If we're approaching -1 from the left, if you imagine the number line, we would be to the left of -1. So we would be somewhere like -1.1. Right? Or maybe even closer, maybe -1.01. But that's kind of where I'm imagining this x value. To the left of -1 means we are a little bit less than -1. I just said we are less than -1. So it's following this rule, 1 plus x. And the limit of 1 plus x as x goes to something, 1 plus x is just a polynomial. So we are allowed to just plug in x. 1 plus x is 1 plus -1. And this is going to give us 0. So what I had to do there, just to recap, was I thought really hard about what x is approaching and from what direction, and it helped me figure out which of these 3 piecewise rules are we following. We're following the first rule. I looked at it. I said it's a polynomial. We had a theorem that said for polynomials, you can just plug in the number. Next part, we're still approaching -1, but this time we're approaching it from the right. If we're a little bit to the right of -1, it means that we are a little bit larger than -1. If we're a little bit larger than -1, then we are in this middle rule. F of x equals x squared if x is between -1 and +1. So what happens to x squared as x goes to -1? It becomes -1 squared, which is 1. Next part, x goes to 1. There's no plus or minus. That means that we're talking about the limit where we have to consider both sides. And again, we have already done the left-hand side and the right-hand side. We got different numbers here. We got a 0 and a 1. So this does not exist because we got different answers for part A and B. If we had gotten the same answer for part A and B, then that would have been the answer to C, because that would be the capital L. Part D, we're approaching +1 from the left. If we're approaching +1 from the left, we are a little bit less than +1. So we're still in this second rule where f of x equals x squared. So we do 1 squared and just get 1. Next problem has us approaching 1 from the right, so we are a little bit larger. we're imagining that we're a little bit larger than 1, we're approaching 1. You know, you imagine it's like 1.1, 1.01, and you get closer and closer and closer and closer, but you are a little bit greater than 1. So you're following the third rule, the one that says 2 minus x. That's a polynomial, so you're allowed to plug in x, and we get 1. Hey, look at this. Part F is asking us for the limit as x goes to 1. We already did the left-hand limit and found 1. We did the right-hand limit and found 1. Therefore, by the theorem, this answer is 1. So when you approach from the left, that's what you get. And when you approach from the right, that's what you get. Pretty cool. We did that without drawing any pictures. I guess you could draw it if you wanted, though. You'd have like a straight line, a parabola, another straight line. But we didn't have to draw it. Okay, so I have one more type of problem that I'd like to show you for this section. And through the magic of video editing, I've already written the problem down here. So this is going to be a different type of problem. Let's see what we've got. I'm giving us a graph. And all right, fine. Looks like maybe some of the types of graphs we've seen. Something seems to be happening around x equals 1, so there's probably going to be a question that might involve that. Graph keeps going towards the left, keeps going towards the right. I could see what some of the x-intercepts are. Looks like here's another x-intercept. At -1, I guess. All right, so what's going to be different about this? Instead of asking you for limits and one-sided limits, I've got some true or false questions. So I'm going to give you 4 of these, and I'm going to give you a little time to think about them. But limits lend themselves pretty nicely to true or false questions. These ones are going to be a little bit different. Let me give you a chance to see all these. True or false, and I'm not asking you for an explanation. I'm just asking you for a true or false. The limit exists for every c in the interval, and so on. So why don't you take a couple of minutes and think about these? All right, so whenever we have something like this, you know, you're welcome to pause the video and work on it some more. I'm going to talk about these, so we just want a true or a false. This is a little bit of a different type of question because it's asking about every c in this interval. Now, one thing I want to say is that in general, most of the limits that we've looked at so far, in not just this question, but in all questions, it seems like most limits that we've looked at do exist. Occasionally, we've had 1 or 2 where we say it does not exist, but overall, most of the limits we see do exist. So now it's asking for like across an entire interval, everything from -3 to -1. All right, let's go. First problem. Does this limit exist for every c in that interval? So I'm looking around -3, thinking about whether the limit exists there, and then I'm looking to the right of it, maybe at like -2, and then over here is -1. So it's only asking about this part of the picture, this little dip. Okay, this little valley. Well, I don't really see any problem points in here. Like, I don't see any weird sudden jumps or any holes in the graph or anything weird going on. At the point -3, I would say yes, the limit does look like it exists, because I think if I were to approach from the left or right, I'd be approaching the same thing. Maybe like down here, x equals -2. I think we would approach from the left or the right, we would get to the same thing. -1, the end point of the interval, I think if we approach from the left or the right, I think we're going to get the same thing. So I'm going to say yes, this is true. The limit does look like it exists. It equals different things at different values in this interval, but it does exist. Next, it's asking us, okay, same interval. Does the limit of the function always equal the function evaluated at c. Now this little equation here looks like this showed up in the previous video when we had a theorem about polynomials and rational functions. It was basically saying for certain types of functions, you could just plug in c. All right, let's look. For this part, we don't know if this is a polynomial per se. Maybe it looks a little bit like a parabola. Okay, visually, if you just asked me to find the limit as x goes to -3, I think I would say that that answer is 0. I would approach from the left, I'd approach from the right, I'd get to a height of 0. That would be the limit. It looks like in this case, that is also f of -3. F of -3 looks like 0. So I'd say yes for that point. We're not going to check every single point in this interval, but just to get an idea, let's look at the middle. When x is -2, I think the limit looks like it would be -1. And I think the function value, f of -2, looks like it would be -1. So yes. And then also, let's check this right endpoint of the interval. The limit, I think, would be 0. Approach from the left, approach from the right, approaching a height of 0. And the function value is 0. It's one of the x-intercepts. So I'm going to say true. I think everywhere on that part of the graph, the limit does equal just f of c. Next part, does the limit exist for every c in this interval? So this is going from -1 to 3. This is probably a more interesting part of the graph. I'm going to draw underneath it and say -1 to +3 is sort of this part of the graph, right? Because here's -1, here's +3. So we're kind of focused in on what's going on. All right, limit looks like it exists here. Looks like it exists here. This looks like a weird place at 1. Let's come back to that. Let's skip that for now and come back to it. I think as we go down this hill, it looks like the limit would exist everywhere here. And 3 is the endpoint, and it does look like the limit exists there. We'd approach from the left or the right, and we'd get the same thing. Let's go back to this weird thing. Does the limit exist? Side note, the limit of this function as x approaches 1, does that exist? And if it exists, what is it? This could be just a little limit problem I give you sometime. We've seen problems like this. All right, what happens when you approach from the left? We're approaching a height of 2. What happens when you approach from the right? Let me zoom in on this maybe. If I approach from the left or the right, either way, I'm approaching a height of 2. This limit is 2. So for the purposes of part C, we just wanted to know, does it exist? And yes, that was the only point in that interval that looked like it might be a questionable point, but the limit does exist there. It equals 2. Now, does the limit as x approaches c, does this limit always equal f of c for every c in this interval? So I've already kind of said that that looked like the only weird point where we need to kind of look at it closely, investigate closely. That's what the limit is. What is f of 1? Like, what if I just plug in 1? There's a point floating up here. That's the point 1, 3, right? So f of 1 is 3. These are not equal to each other. So you could say this is a side note, or you could say this is scratch work for parts C and D. So that makes this false, because we just found a place in that interval where the limit does not equal f of c. Okay, so we're going to be wrapping up in just a moment here. I'll give you just another chance in case you're writing any of this down. Okay, so if that last question seemed a little weird to you, if you had any confusion about those true or false questions, I'll tell you that that whole question is designed to kind of lead us into the next topic. So the next video that you see, which is going to be on a topic called continuity, it's going to discuss that sort of thing a little bit in a little bit more detail. Okay, so if that problem seemed a little weird, the next video might help a little bit with that problem. Okay, so that's going to be it for this one. Overall, this lesson was one of the ones that's a little bit shorter. So I'll see you next time, and take care.